In the setup for the calculation of thermal energy, or Q, the value with the fewest number of significant figures is at M, C, or delta T. Well, hopefully you can see in the setup it's going to be the change in temperature, the delta T, which has only two significant figures. So 0.79 has only two significant figures, and the calculated value for Q should be reported with two significant figures. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 6.1 to 6.4. As you can see on this slide, these topics fall under Unit 6 in the AP Chemistry curriculum, Thermochemistry. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 6.1, endothermic and exothermic processes. Here are some essential knowledge statements from the AP Chemistry course and exam description. Temperature changes in a system indicate energy changes. Energy changes in a system can be described as endothermic and exothermic processes, such as the heating or cooling of a substance, phase changes, or chemical transformations. When a chemical reaction occurs, the energy of the system either decreases for an exothermic reaction, increases for an endothermic reaction, or remains the same. For exothermic reactions, the energy lost by the reacting species, or the system, is gained by the surroundings as heat transfer from or work done by the system. Likewise, for endothermic reactions, the system gains energy from the surroundings by heat transfer to or work done on the system. The formation of a solution may be an exothermic or an endothermic process depending on the relative strengths of intermolecular or interparticle interactions before and after the dissolution process. Now let's move on to the practice for topic 6.1. This is question 1. In question 1, it says, a student conducts an experiment in which a sample of sodium bicarbonate, NaHCO3 solid, is added to a solution of acetic acid, HC2H3O2 aqueous, in a coffee cup calorimeter. The reaction is represented by the equation shown above. The student observes the formation of bubbles when the two substances are combined and stirs the mixture until the solid dissolves completely. The temperature of the reaction mixture is recorded every 15 seconds. Data from the experiment is shown in the table below. So we can see a data table in which the initial temperature of the reaction mixture at time 0 is 25 degrees Celsius, and then we can see that the temperature decreases over time, and at 120 seconds, the temperature has decreased to 19.2 degrees Celsius. So with this decrease in temperature, the student makes the claim that the reaction is exothermic because the temperature of the solution decreases as the reaction proceeds. Do you agree or disagree with the student's claim? Justify your answer. Now, before I show you the answer to question 1, I'd like to show you something that I had shared in my video for topics 6.1 to 6.5. And so what you're looking at is something I had presented in that video. If a temperature change occurs during the process of forming a solution or during a chemical reaction, it is important to understand the direction of heat flow between the system and the surroundings. This information is summarized in the following table. Note that the thermometer is usually considered to be part of the surroundings and not the system. So, for example, suppose that during the process, the temperature decreases. What's the direction of heat flow if the temperature decreases? Well, heat flows from the surroundings into the system. And as you can see on this slide, if I have an instant cold pack, heat flows from the surroundings to the system. The temperature of the surroundings decreases, and as we put our hand on the surface of that instant cold pack, it feels cold. That would be an endothermic process, and the temperature of the surroundings decreases. Now, on the other hand, suppose that during a certain process, the temperature increases. Well, now we would say that heat flows from the system into the surroundings. So again, here's an example of an instant hot pack. Heat flows from the system to the surroundings. The temperature of the surroundings increases. We place our hand on the surface of that instant hot pack, and it feels hot. So to summarize, we have a decrease in temperature, endothermic process. We have an increase in temperature, exothermic process. So in question 1, the student makes the claim that the reaction is exothermic because the temperature of the solution decreases. So we should disagree with the student's claim. So what I said was that this reaction should be classified as endothermic because the temperature decreases as the reaction proceeds. Thermal energy is transferred from the surroundings to the system. So remember that the thermometer is generally considered to be part of the surroundings with these type of situations. The temperature of the surroundings decreases because the surroundings experience a decrease in thermal energy. Now, before I show you question 2 of this packet, I'd like to present to you a similar question from the 2023 AP Chemistry Free Response questions. So this is part F of question 3 from the 2023 AP Chemistry exam. And what you're looking at is a different chemical reaction, but you can see that there is a table with time and temperature. The temperature starts out at 21.20 degrees Celsius at time 0, and then it increases to a temperature of 21.90 degrees Celsius after a period of 100 seconds. So it's a similar question, and it says, is the reaction endothermic or exothermic? Justify your answer using the information in the table. Now I'll show you the official scoring guidelines answer, and I've included a link in the video description area for not only the 2023 AP Chemistry free response questions, but also the official scoring guidelines for those questions. So according to the official scoring guidelines, this reaction from the 2023 exam, question 3, part F, should be classified as exothermic. And again, they're using the information in the table and saying the solution temperature increases as the reaction proceeds. Now what I normally do is I show you not only the official scoring guidelines answer, but I also show you examples of common student mistakes. So take a look. On the right side of this slide, the official answer to that question was that the reaction is exothermic because the temperature of the solution is increasing, which means that the reaction is releasing heat to the surroundings or to the solution. But one common error on this question was assuming that because the temperature is increasing, that it was endothermic, and that's incorrect. Another common error was providing a heat exchange explanation for why the reaction is exothermic without ever referencing the data in the table as required by the question. So in other words, the student might have said it's exothermic because heat is released or heat is being transferred from the system to the surroundings, but as it mentions, justify your answer using the information in the table if you see that on the AP Chemistry exam, then that's what they're looking for in your response. All right, now back to question 1 of this packet. Again, we disagree with the student's claim. The temperature during this reaction between sodium bicarbonate and acetic acid should be classified as endothermic because, as we can see in the data table, the temperature decreases as the reaction proceeds. Now, let's take a look at question 2 in this packet. And we can see in question 2 that this also involves a temperature change. In question 2, it says a student dissolves a sample of solid lithium chloride into a sample of water in a coffee cup calorimeter. The solid dissolves completely, and the student monitors the temperature of the solution, observing that the temperature increases from 21 degrees Celsius to 32 degrees Celsius. Which of the following best helps to explain the energy change that occurred during the dissolution of solid lithium chloride? Now, unlike question 1, in which the temperature decreases, here in question 2, the temperature increases. So we can say that the dissolution of lithium chloride in water should be classified as exothermic because the solution temperature increases during the dissolution process. Thermal energy is transferred from the system to the surroundings. The temperature of the solution increases because the surroundings experience an increase in thermal energy. And now that we know that the dissolution of lithium chloride is exothermic, let's go ahead and consider these 4 answer choices. Which of the following best helps to explain that energy was released during the dissolution of solid lithium chloride? I'll start with choice A. Now, in choice A, it says that when solid lithium chloride dissolves in water, ions of lithium and chloride are formed. But it doesn't actually specifically refer to energy, and there's no discussion of attractive forces between particles that may be broken or formed during the dissolution of lithium chloride in water. So that statement in choice A is not going to explain the exothermic nature of the dissolution, so we can go ahead and eliminate choice A. Now, before I take a look at the details of choices B, C, and D, I'll show you something I had presented in my video for topic 6.1. So here is a particle diagram that breaks down the dissolution of an ionic solute in a polar solvent such as water. And it's breaking it down in this particle diagram into 3 steps. So we have step 1, attractive forces between the ions and the crystal lattice of that ionic solute are broken. Step 2, we are breaking some of the attractive forces between the polar molecules of the solvent. And then in step 3, the solute and the solvent are coming together, and attractive forces between the ions and the polar molecules of the solvent are formed. Now, each of these processes can be classified as either endothermic or exothermic. So you should know that breaking attractive forces between particles is an endothermic process, whereas forming attractive forces between particles is an exothermic process. So this information will guide us as we consider the answer choices in question 2 of this packet. So looking at choices B and C, it talks about attractions between water molecules and attractions between ions in the crystal lattice. So in choice B, attractive forces between water molecules would be broken during the dissolution process, and that would be an endothermic process. But since the dissolution of lithium chloride in water is classified as exothermic, then choice B would not explain the energy change that occurred during the dissolution of lithium chloride. So we can eliminate choice B. Similarly, attractive forces between ions in the crystal lattice would also be broken during the dissolution of lithium chloride, and that would be an endothermic process, so you're breaking attractive forces, and again, that would not explain why the dissolution of lithium chloride is actually exothermic. So we can eliminate choice C. So why is choice D the correct answer? Well, it talks about the ion-dipole interactions, so attractions between the ions and the polar water molecules. So the reason why choice D is the correct answer to question 2 is because attractive forces between lithium ions and water molecules are formed during the dissolution of lithium chloride. And forming attractive forces is an exothermic process, and this would best help to explain why the dissolution of lithium chloride is classified as an exothermic process. All right, well, hopefully that explanation makes sense. Now, let's move on to the review for topic 6.2, energy diagrams. Here is a very brief essential knowledge statement from the AP Chemistry course and exam description. A physical or chemical process can be described with an energy diagram that shows the endothermic or exothermic nature of that process. Now let's move on to the practice for topic 6.2. This is question 3. In question 3, it says, the diagram above shows the reaction energy profile for the reaction represented by the following equation. X2 plus 2y2 produces 2xy2. And the question asks, which of the following best describes this chemical reaction and the flow of heat as the reaction occurs? Now we can look at the 4 answer choices for question 3, and we can see that 2 choices classify the reaction as endothermic, and 2 choices classify this reaction as exothermic. So let's go ahead and begin by classifying the reaction. We can see in this diagram that the potential energy of the products is less than the potential energy of the reactants. And you may recall in an earlier episode of AP Chemistry Review and Practice, when I was talking about topic 5.6, reaction energy profile, I had mentioned the following information. So if a chemical reaction is classified as exothermic, the potential energy of the products is less than the potential energy of the reactants. And that's actually what we are observing in question 3 of this packet. So exothermic is the correct classification of this reaction. But just to show you, on the other hand, if a reaction is classified as endothermic, then we would see in the reaction energy profile that the potential energy of the products would be greater than the potential energy of the reactants. So again, in question 3, we can say with confidence that this reaction is exothermic because the potential energy of the products is less than the potential energy of the reactants. So now let's go ahead and eliminate choices A and C because they say endothermic. Now we have to decide whether the correct answer to question 3 involves heat transfer from the system to the surroundings or from the surroundings to the system. So I'll show you something I had mentioned earlier in this lesson. For topic 6.1, endothermic and exothermic processes, if the reaction is exothermic, then the energy is lost by the system and gained by the surroundings. So the correct answer to question 3 is this reaction is exothermic and heat is transferred from the system to the surroundings. Now, before I move on to the review for topic 6.3, I wanted to show you an example of a diagram. This comes from the 2018 AP Chemistry Free Response questions. Again, I've included a link in the video description area to the 2018 free response questions as well as the official scoring guidelines. So what I'm focusing on is this diagram. This diagram shows temperature on the y-axis and time on the x-axis. So I wanted to show you that this diagram is not a reaction energy profile. This is a graph that shows that the temperature of the reaction mixture increases as the reaction proceeds. So be careful when you're looking at a diagram to make sure that you're not confusing a change in temperature with a change in potential energy. So this diagram would actually indicate an exothermic process because the temperature of the reaction mixture increases as the reaction proceeds. So just make sure that you are very clear when you're looking at a diagram to focus on the label for the y-axis and the x-axis. So this diagram is not potential energy versus the reaction coordinate. Instead, this diagram shows temperature versus time. So just be careful and pay attention to the labels on the x and y axis. All right, now it's time to move on to the review for topic 6.3, heat transfer and thermal equilibrium. Here are some essential knowledge statements from the AP Chemistry course and exam description. The particles in a warmer body have a greater average kinetic energy than those in a cooler body. Collisions between particles in thermal contact can result in the transfer of energy. This process is called heat transfer, heat exchange, or transfer of energy as heat. Eventually, thermal equilibrium is reached as the particles continue to collide. At thermal equilibrium, the average kinetic energy of both bodies is the same, and hence their temperatures are the same. Now let's move on to the practice for topic 6.3. This is question 4. In question 4, it says, a student places a metal cube in boiling water, so its temperature will be 100 degrees Celsius. The student then places the metal cube into a calorimeter that contains water. The student records the highest temperature of the water. Data from the experiment is shown in the table below. So we can see in this data table that the initial temperature of the metal cube is 100 degrees Celsius. The initial temperature of the water is 25 degrees Celsius. And then we can see that the highest temperature of the water is 32.6 degrees Celsius. Now there are some particle diagrams with arrows in question 4, but before we take a look at these particle diagrams, I'd like to show you something I had presented in my video for topic 6.3. So what you're looking at is a diagram in which a piece of metal is heated to a temperature of 100 degrees Celsius in a boiling water bath. And then the hot metal is quickly transferred to a sample of water at 20 degrees Celsius in an insulated container or a calorimeter. And so what was asking in this question from my video for topic 6.3 is to describe the direction of the heat flow at the moment that the sample of metal is added to the sample of water. So heat normally flows from a warmer object to a cooler object. So at the moment that the hot metal is added to the cooler water, the heat would flow from the warmer piece of metal at 100 degrees Celsius to the cooler water molecules around it at 20 degrees Celsius. And then at some point during the experiment, the transfer of heat between the metal and the water would be complete when thermal equilibrium is reached and the two substances are at the same temperature. So heat transfer will be complete when thermal equilibrium is reached and the temperature of the metal and the water are the same value. All right, well now let's go back to question 4 in this packet. So we've got our information. Let's take a look at the particle diagrams with the arrows. And so the information with these 3 particle diagrams is the following. 3 diagrams are shown below that represent particle level views of water molecules in the calorimeter before and after the metal cube was added. The length of the arrows represent the speed of the water molecules in the system. In other words, longer arrows represent a faster speed, and shorter arrows represent a slower speed. So the question in part A of question 4 is, which diagram, number 1, number 2, or number 3, best illustrates how the speed of the water molecules is affected after the metal cube is added to the calorimeter? Justify your answer in terms of the change in the temperature of the water that occurs during this experiment. So we know that the temperature of the water increased from 25 degrees Celsius to 32.6 degrees Celsius. And if the temperature of the water increased, we are looking for a faster speed of the water molecules, and that would be longer arrows in the diagram. Now in diagram number 1, if I focus on the arrows in the before picture, and I look at the arrows in the after picture, I don't see any difference. So the arrows are the same length, no change in temperature. So that's not the best choice. I'm looking for a faster speed with longer arrows. Now in diagram 2, the length of the arrows has changed, but in the wrong direction that we're looking for. So we can see in the after picture, those arrows are actually shorter in length, and that would indicate that the temperature of the water has decreased because the speed is slower. So that's not the correct diagram that we're looking for. It's going to be diagram number 3. So if you focus on the arrows in the before versus the after picture, we can see that in the after picture, those are longer arrows representing a faster speed and an increase in temperature. So the answer to part A of question 4 is the following. Diagram 3 best illustrates how the speed of the water molecules is affected after the metal cube is added to the calorimeter. Since the temperature of the water increases during this experiment, the average speed of the molecules should increase as indicated by the longer arrows in the after particle diagram on the right. Now let's take a look at part B of question 4, which says, a student makes the claim that at the moment that the metal cube is added to the water, thermal energy is transferred from the metal to the water. Do you agree or disagree with the student's claim? Justify your answer in terms of the initial temperature of the metal and the initial temperature of the water before they are combined. So we know that heat normally flows from the warmer object to the cooler object, and that's exactly what's happening in this experiment. From the metal to the water makes sense because the initial temperature of the metal is 100 degrees Celsius and the initial temperature of the water is 25 degrees Celsius. So yes, I agree with the student's claim. The initial temperature of the metal cube is 100 degrees Celsius and the initial temperature of the water is 25 degrees Celsius. Thermal energy should flow from the warmer substance, the metal, to the cooler substance, the water. All right, well, those are the answers to question 4. Now let's take a look at question 5, which is a multiple choice question. In question 5, it says, a 1 mole sample of helium gas at 20 degrees Celsius is mixed with a 1 mole sample of neon gas at 80 degrees Celsius. Which of the following correctly predicts how the temperature of the helium sample and the average kinetic energy of the helium atoms will be affected as the mixture approaches thermal equilibrium? So considering the fact that heat or thermal energy normally flows from the warmer object to the cooler object, in this case, the thermal energy should flow from the warmer substance, which is neon at 80 degrees Celsius, to the cooler substance, helium, at 20 degrees Celsius. Therefore, the temperature of the helium sample should increase. And if the temperature of the helium sample should increase, that means that the correct answer is either choice B or choice D. So we can eliminate choices A and C. Now, with respect to the average kinetic energy of the helium atoms, I'm going to remind you of something I had presented in an earlier lesson in AP Chemistry Review and Practice. This was when I was discussing topic 3.5, kinetic molecular theory. And one of the essential knowledge statements is that the Kelvin temperature of a sample of matter is proportional to the average kinetic energy of the particles. So that means higher temperature, higher average kinetic energy. So looking at the two choices, B and D, we would consider that since the temperature of the helium sample is increasing, the average kinetic energy of the helium atoms will also increase. And that's because the temperature of a sample of matter is proportional to the average kinetic energy of the particles in the sample. So the correct answer to question 5 is choice D. Now, before we move on to the review for topic 6.4, I'd like to show you another example of an AP Chemistry free response question that's relevant to this topic. And you can see this is from the 2024 AP Chemistry free response questions. This is question 4, and I'm going to show you parts A and B for now, and then I will show you parts C and D later in this lesson. So the first part of this question was simply based on the skill of knowing how to read the temperature on this thermometer according to the precision of the thermometer. So as you can look at this diagram with a number of 30 and 40, there are 10 spaces in between 30 and 40. So each line printed on this thermometer is worth 1 degree Celsius. And the temperature for part A of this question is somewhere between 38 and 39. But if I estimate that the temperature is halfway between 38 and 39, then I would correctly read 38.5 degrees Celsius. And that's my answer to part A. Now, looking at the information on this slide, we can see that the correct answer would be approximately 38.5 plus or minus 0.1 degrees Celsius, but the mistake that students made was not recognizing that each mark on the thermometer between 30 and 40 degrees represents 1 degree Celsius. So some students, when they looked at this scale, they thought that each line was worth 0.1, so they might have read the temperature incorrectly as 30.85 instead of 38.5. So that was a mistake, that they didn't quite read the thermometer correctly. Now, the next part of this question, so part B, does involve arrows like I showed you in question 4 of this packet. But in this question, the students had to draw the arrows themselves. So they had to indicate whether those arrows were longer or shorter. And since the temperature of the water was increasing, they were looking for longer arrows in this diagram. So the intended student response was to show that the average length of the arrows was longer in the after picture compared to the before picture. And so one mistake was not recognizing that the temperature increase corresponds to an increase in average particle speed. And some students did not connect this question with the information given in part A, and they didn't realize that the temperature of the water was increasing, and they had to show longer arrows. Again, I will show you parts C and D of this question a little bit later in this lesson. Now it is time to move on to the review for topic 6.4, heat capacity and calorimetry. Here are some essential knowledge statements from the AP Chemistry course and exam description. The heating of a cool body by a warmer body is an important form of energy transfer between two systems, and the amount of heat transferred between two bodies may be quantified by the heat transfer equation Q equals M times C times delta T. Calorimetry experiments are used to measure the transfer of heat, and I'll just show you, this is a view of the AP Chemistry equations and constant sheet that in the section entitled Thermodynamics and Electrochemistry, you can see that equation. So Q equals MC delta T, where Q is heat, M is mass, C is specific heat capacity, and T is temperature. So delta T is the change in temperature. The first law of thermodynamics states that energy is conserved in chemical and physical processes. The transfer of a given amount of thermal energy will not produce the same temperature change in equal masses of matter with differing specific heat capacities. Heating a system increases the energy of the system, while cooling a system decreases the energy of the system. The specific heat capacity of a substance and the molar heat capacity are both used in energy calculations. Chemical systems change their energy through three main processes: heating and cooling, phase transitions, and chemical reactions. In calorimetry experiments involving dissolution, temperature changes of the mixture within the calorimeter can be used to determine the direction of energy flow. So if the temperature of the mixture increases, thermal energy is released by the dissolution process, and that would be exothermic. On the other hand, if the temperature of the mixture decreases, then thermal energy is absorbed by the dissolution process, and that would be endothermic. Now it's time to move on to the practice for topic 6.4. This is question 6. In question 6, we are given a data table with 4 different substances: aluminum, copper, iron, and lead, and each substance has a value for its specific heat capacity, which has units of joules per gram degrees Celsius. So we're going to do our calculations involving the equation Q equals M times C times delta T, and question 6 asks, based on the information in the table above, which of the following experiments absorbs the greatest quantity of thermal energy? So Q equals MC delta T for choice A, that would be a mass of 10 grams of aluminum, specific heat capacity of 0.90 joules per gram degree Celsius, and changing from 20 degrees Celsius to 40 degrees Celsius, that is a change or a delta T of 20 degrees Celsius. So 10 times 0.90 times 20, that gives us a value of 180 joules. And the units are joules because grams and degrees Celsius cancel out. So that would be the amount of thermal energy. Now moving on to choice B, we have a mass of 10 grams of copper. The specific heat capacity is 0.39 joules per gram degrees Celsius. And changing from 20 degrees Celsius to 50 degrees Celsius, that would be a difference or a change of 30 degrees Celsius. So 10 times 0.39 times 30, and we get approximately 117 joules. Now, in choice C, we have a sample of iron. The mass of that sample of iron is 20 grams. We have a specific heat capacity of 0.45 joules per gram degrees Celsius, and changing from 20 degrees Celsius to 35 degrees Celsius, that's a difference or a change of 15 degrees Celsius. So 20 times 0.45 times 15, and we get approximately 135 joules. And then finally in choice D, we have a sample of lead. It has a mass of 20 grams, and then 0.13 joules per gram degrees Celsius, that's the specific heat capacity. And we're changing from 20 degrees Celsius to 70 degrees Celsius. That's a difference or a change in temperature of 50. So it's going to be 20 times 0.13 times 50, and we get approximately 130 joules. So looking at these four answer choices in our calculations, we can see that the correct answer to question 6 is choice A, because it involves the greatest quantity of thermal energy. All right, well, hopefully that explanation and calculations make sense to you. Now it's time to move on to question 7. In question 7, it says a student adds a sample of metal to a sample of water in a calorimeter. Data from the experiment is shown in the table below. Assume that the calorimeter is perfectly insulated. So we can see that the initial temperature of the metal in this experiment is 90 degrees Celsius, but then when the metal and the water reach a state of thermal equilibrium at the end of the experiment, the final temperature is 23 degrees Celsius. So that's a difference of 67 degrees Celsius. That's the magnitude of the change in temperature, or the delta T for the metal. Now for the water begins at a temperature initially of 21 degrees Celsius, and then the final temperature of the water is 23 degrees Celsius, so that's a difference of 2 degrees. So based on this observation that the magnitude of delta T for the metal is 67 degrees Celsius, whereas the magnitude of the delta T for the water is 2 degrees Celsius, a student makes the claim that the quantity of thermal energy lost by the metal is greater than the quantity of thermal energy gained by the water. And the question says, do you agree or disagree with the student's claim? Justify your answer. Now, before I answer part A of question 7, I'll remind you of a couple of essential knowledge statements for topic 6.4. And the first one that I'm highlighting is that the first law of thermodynamics, which is also known as the law of conservation of energy, states that energy is conserved in chemical and physical processes. So what does that mean for this experiment in which a hot sample of metal is added to a cooler sample of water? It means that the energy that is lost by the metal is equal to the energy gained by the water. And then I will also mention that when you have a situation in which you have the same amount of thermal energy for two different substances, they would not produce the same temperature change, even when you have equal masses. So it's that difference in the specific heat capacity that will affect the magnitude of delta T, even when you have the same mass and the same amount of heat or thermal energy. All right, now back to the answer to part A of question 7. So this is what I wrote for my answer to part A based on the law of conservation of energy. I said, I disagree with the student's claim. According to the first law of thermodynamics, also referred to as the law of conservation of energy, the amount of thermal energy or heat lost by the metal in this experiment is equal to the amount of thermal energy or heat gained by the water. Now, if you're looking at the data in this table, you will notice that it says the specific heat capacity of water is 4.18 joules per gram degree Celsius. But you don't see a value for the specific heat capacity of the metal, and that's because we need to calculate that value. So part B of this question says, based on the data in the table, calculate the specific heat capacity of the metal in units of joules per gram degree Celsius. We can set up an equation in which the thermal energy lost by the metal is equal to the thermal energy gained by the water. So what I'm going to do is I'm not going to use any signs, positive or negative signs, to indicate the loss of heat or the gain of heat, and I'm not going to use any signs for my delta T. I'm going to treat the Q, or the heat, and the delta T as an absolute value. I'm only going to focus on the magnitude or the absolute value. I'm not going to focus on positive or negative signs. So what I have is M times C times delta T for the metal is equal to M times C times delta T for the water. And the only quantity out of these 6 quantities that I don't know is C, or the specific heat capacity for the metal. So that's what I'm trying to calculate in part B of question 7. So the M for the metal is 25 grams. The C, or the specific heat capacity of the metal, is, well, we don't know. That's what we're trying to find. The delta T for the metal would be based on that difference of 90 degrees Celsius initial temperature and 23 degrees Celsius final temperature, and that's a difference of 67 degrees Celsius. Now on the other side of the equation, the M for the water is 75 grams. The specific heat capacity of the water is 4.18 joules per gram degree Celsius, and the delta T for the water is based on that difference of 23 and 21. That's a difference of 2 degrees Celsius. So you can see that all we have to do now is a little bit of algebra to solve for C, or the specific heat capacity of the metal. So I'm going to divide both sides of this equation by the product of 25 and 67. So the value for the specific heat capacity of the metal would be obtained by putting the following information into my calculator. 75 times 4.18 times 2 divided by 25 divided by 67. And when I put this into my calculator, I get a value of 0.374328. My units are joules per gram degree Celsius. Now, of course, this is way too many significant figures. So based on the numbers that I'm using in terms of my measurements, my calculations, I think 2 significant figures would be what limits me. So I'll say 0.37 joules per gram degree Celsius. So that is the answer to part B of question 7. Hopefully that makes sense. Now, before we move on to question 8 in this packet, I'd like to show you the remaining parts of that FRQ, that free response question number 4. So you may recall that in part A of this question, the temperature on the thermometer, the final temperature when the metal and the water reached thermal equilibrium in that experiment, was 38.5 degrees. So let me show you what part C of this question looks like. It says, assuming that the metal transfers 2,940 joules of thermal energy to the water, calculate the specific heat, or the specific heat capacity, of the metal in units of joules per gram degree Celsius. So considering that we have our data table in which the final temperature is 38.5 degrees, we should have enough information to calculate the value of C, or the specific heat capacity of the metal. So what is our amount of heat in our Q equals mc delta T? Well, that was given to us in this problem. That's 2,940 joules. The mass of the metal cube is listed as 98.1 grams. The specific heat capacity of the metal is, we don't know, we're trying to calculate that. And the difference in temperature would be 100 minus 38.5, so that's a difference of 61.5 degrees Celsius. Now, when I pick up my calculator to solve for the value of C, it's going to be 2,940 divided by the product of 98.1 and 61.5. And so when I do that math, 2,940 divided by 98.1 divided by 61.5, I get 0.487 joules per gram degree Celsius. Now, I'll show you the official scoring guidelines for the 2024 AP free response questions. All of this information is included in the video description area. So the 2024 FRQs and the official scoring guidelines, you can find that in the video description area. So this was the official scoring guidelines answer. You can see 0.487 joules per gram degree Celsius was the intended answer to FRQ number 4, part C. Now, with respect to the intended answer, which you can see I'm highlighting in that green rectangle on the right side of this slide, here are some examples of common mistakes that students made. Some students, they used the wrong delta T. So what they did was the delta T for the water instead of the delta T for the metal, or some of them simply subtracted the initial temperature of the metal minus the initial temperature of the water. So they had the wrong delta T. Another mistake that students made is that they didn't actually calculate the change in temperature by doing the difference in temperature for the metal. Some students did not understand in their calculations that the value of C, the specific heat capacity, cannot be expressed as a negative number. And then the last example of mistakes that students made simply involved algebraic errors. So as you're doing your calculations on the AP Chemistry exam, yes, you should pay attention to units, and you should take your time and be careful not to make any careless algebra errors in the setup for your calculation. All right, there was one more part of this question. This is FRQ number 4 from the 2024 AP Chemistry exam. So part D of this question says the following. In a second experiment, 2,940 joules of thermal energy is transferred from 98.1 grams of aluminum, which has a specific heat capacity of 0.897 joules per gram degree Celsius. So the intent of this question was to help students somehow connect the results of this experiment to what would happen if we have a different metal other than the metal that was used in the previous experiment. And so the question asks, explain how the magnitude of the temperature change of the aluminum compares with the magnitude of the temperature change of the metal in the original experiment. So the purpose of this question is to see if students understand how to connect the C and the delta T, because that's what's going to be different when you compare these two experiments. So Q equals M times C times delta T. And in the original experiment, it was 2,940 joules. It was 98.1 grams of the metal, and we had calculated 0.487 joules per gram degree Celsius in part C of this question. And the delta T for the metal was 61.5 degrees Celsius. But now in part D of this question, with the aluminum, we have the same amount of heat, so the same value of Q. We have the same mass of the metal sample, but we should be able to recognize that if there's a different value for the specific heat capacity of the metal, it will affect the value of delta T for the aluminum. So there's an inverse relationship between the specific heat capacity and the change in temperature. So when I say that there's an inverse relationship between C and delta T, what I mean is that as a larger value of C would result in a smaller value of delta T, that is the intent of part D of this question. So the value of delta T for the aluminum should be less than 61.5 degrees Celsius, and that's because we have a larger value of C and we would expect a smaller value of delta T. So I'll show you the official scoring guidelines for this question. So for a valid explanation consistent with part C, accept one of the following. So in words, the student could say that the value of the change in temperature for the aluminum will be smaller because aluminum has a greater specific heat capacity than the metal in the original experiment. Therefore, the same thermal energy transfer applied to the same mass will result in a smaller change in temperature according to the equation Q equals mc delta T. What the student could also do to earn credit is to actually show their calculations. So 2,940 joules divided by 98.1 grams divided by 0.897 joules per gram degree Celsius, that would give us a delta T of 33.4 degrees Celsius, which is less than the delta T of 61.5 degrees Celsius from the original experiment. Now let's take a look at some examples of common mistakes that students made. And so one example is not understanding the inverse relationship between specific heat and temperature change when the mass and the quantity of heat are constant. Another mistake that students made is they incorrectly used an inequality sign. For example, they meant to say less than, but they wrote the symbol for greater than. Or they made a mistake of relating specific heat to time or rate. So they were talking about faster and slower and talking about the rate of change in temperature as opposed to focusing on the magnitude of the temperature change. So not understanding the term magnitude, they were somehow confused with their positive and negative signs. They were referring to a positive temperature change rather than comparing the magnitudes of the changes. And then the last mistake that students made was failing to use appropriate vocabulary, such as confusing heat and temperature, or they would refer to the temperature being larger or smaller instead of referring to the change in temperature. Another mistake that is very common on the AP Chemistry exam, so I strongly encourage you to avoid this situation, is students tend to use the word it in their response. And now it becomes unclear whether the student is referring to the metal or the aluminum. So instead of saying something vague, such as it would have a smaller delta T, you should be specific when you write your explanations and justifications on the AP Chemistry exam. All right, well, that was question 4 from the 2024 AP Chemistry exam. Now it's time to take a look at question 8 in this packet. In question 8, we are given a calorimetry problem which states that the specific heat capacity of liquid water is 4.18 joules per gram degree Celsius. A 35.0 gram sample of liquid water, initially at 10.0 degrees Celsius, absorbs 12.3 kilojoules of heat. Calculate the final temperature of the sample of liquid water. And so in question 8, it says a student was given the calorimetry problem shown above, and the student set up the calculation as follows. Now we can see the setup for the student's work, and we can see that the final temperature is 10.1 degrees Celsius. But part A of question 8 says that the student's answer of 10.1 degrees Celsius is incorrect. Identify the error in the setup for the student's calculation that explains why the calculated value for the final temperature of the sample of liquid water is incorrect. So I wrote this question to encourage you to avoid this kind of situation on the AP Chemistry exam. So when students tend to be in a rush, in a hurry, they tend to neglect to write the units in the setup for their calculation. And so that led to a mistake. Now, if you are in a habit of neglecting to write your units in the setup for your calculation, then you increase the probability or the likelihood of making a mistake, such as what this student has done in this setup. Now, if you're watching this video and you haven't yet found the mistake that the student made, I think you'll find it in a moment, because what I'm going to do is go ahead and show the units for all of these quantities. So the amount of heat that was absorbed by the water was 12.3 kilojoules. The mass of the water is 35.0 grams. The specific heat capacity of the water is 4.18 joules per gram degree Celsius. And then we're solving for the delta T, the change in temperature. So now hopefully you can see that the problem is with the units of energy. So on the left side of the equation, we have 12.3 kilojoules. But on the right side of the equation, we have a specific heat capacity, which is 4.18 joules per gram degree Celsius. So either I need to convert kilojoules into joules, or I need to convert joules into kilojoules, because right now, these units of energy, they don't match each other. So I'm going to choose to convert my kilojoules into joules. So that means I'm going to multiply by 1,000, so 12.3 kilojoules. Here's my conversion factor to go from kilojoules to joules. There's 1,000 joules in 1 kilojoule. So now that would be a quantity of thermal energy, which is actually 12,300 joules. Now, when I finish off this calculation, I'm going to divide both sides of the equation by the product of 35 and 4.18. And when I do this math on my calculator to solve for the change in temperature, it's going to be 12,300 joules divided by 35.0 grams divided by 4.18 joules per gram degree Celsius. And rounding off to 3 significant figures, I get a delta T of 84.1. Now, that's not my final answer for the final temperature of the sample of water, but that is the change in temperature. So the initial temperature of the water before it was heated was 10.0 degrees Celsius. So 10.0 plus 84.1, that gives me a final temperature of the water of 94.1 degrees Celsius. That's very different than the student's incorrect answer of 10.1 degrees Celsius. So let me go back and answer part A of question 8. So it says, identify the error in the setup for the student's calculation, and this is the answer. The student neglected to show any units in the setup for their calculation. So the units of heat, or Q, are kilojoules, but the units of the specific heat capacity, C, are joules per gram degree Celsius. And in part B of this question, it says, calculate the correct value for the final temperature of the sample of liquid water. Show the correct setup for the calculation in the space below. So there's the setup for my delta T, which works out to be 84.1 degrees Celsius. And the final temperature of the liquid water is actually 94.1 degrees Celsius. All right, well, those are the answers to question 8 in this packet. Now let's take a look at question 9. In question 9, it says a student conducts a calorimetry experiment to determine the enthalpy of solution for NH4Cl, and that's ammonium chloride, which dissolves in water according to the equation shown above. The student dissolves a sample of solid ammonium chloride in water in a coffee cup calorimeter. The data from the experiment is shown in the table below. Now, if you're watching this video and you're not exactly sure what enthalpy or enthalpy of solution is, I will tell you that in my next episode of AP Chemistry Review and Practice, I will focus on topics 6.5 and 6.6. And in topic 6.6, it's entitled Introduction to Enthalpy of Reaction. So more is coming about enthalpy in our next episode of AP Chemistry Review and Practice. Now, as you will see in this problem, one distinction between the Q, or the thermal energy or the heat, and the change in enthalpy is that normally Q, or heat, is measured in units of joules or kilojoules, whereas the change in enthalpy, which is symbolized by the delta H, and you'll see that in this question, it's normally kilojoules per mole, or kilojoules per mole of reaction. So again, I will have more to say about the delta H, or the change in enthalpy, in my next episode of AP Chemistry Review and Practice. Now, in this question, let's focus our attention on the change in temperature, so we can see that before the solid ammonium chloride was dissolved in water, the initial temperature of the water was 20 degrees Celsius, and then after all of the solid ammonium chloride dissolved, the final temperature of the solution was 19.21 degrees Celsius. So in part A of question 9, it asks, is the dissolution of ammonium chloride in water classified as an endothermic process or an exothermic process? Justify your answer using the information in the table. Now, specifically, we are going to focus on that change in temperature, and the temperature decreases when ammonium chloride dissolves in water. One of the essential knowledge statements for topic 6.4 says that in calorimetry experiments involving dissolution, which is what is happening here in question 9, temperature changes of the mixture within the calorimeter can be used to determine the direction of energy flow. Now, if the temperature of the mixture increases, then thermal energy is released by the dissolution process, and that would be exothermic. But that's not what's happening here in this experiment in question 9. So what's happening here in question 9 is that the temperature of the mixture is decreasing. And if that happens, thermal energy is absorbed by the dissolution process, and that would be endothermic. So here is the answer to part A of question 9. The dissolution of ammonium chloride in water should be classified as an endothermic process because the temperature of the solution decreases during the dissolution process. Thermal energy is transferred from the surroundings to the system. The temperature of the surroundings decreases because the surroundings experiences a decrease in thermal energy. So if dissolving a solid in water causes the temperature to increase, then that would be exothermic. But if dissolving a solid in water causes the temperature to decrease, which is what is happening in this experiment, then that would be classified as an endothermic process. Now let's go ahead and do some calculations involving Q equals mc delta T. Let's move on to part B of question 9. It says calculate the magnitude of thermal energy, Q, in kilojoules that was transferred in the dissolution of ammonium chloride. Now you might be wondering, there are two different masses listed in this table. We have the mass of water, which is 105.23 grams, and we also have the mass of solid ammonium chloride, which is 1.25 grams. You might be wondering, do I use the mass of the ammonium chloride, or do I use the mass of the water? And the correct answer is actually you have to add them together. So if you're doing a calculation involving Q equals mc delta T to calculate the magnitude of thermal energy that is transferred in the dissolution of a solid, you don't use the mass of just the solid. You don't use the mass of just the water. You add them together. So in this mc delta T, the m should be the mass of the entire solution. So not just the solute, not just the solvent, but both of them added together. The mass of the entire solution should be used in our Q equals mc delta T calculation. That means that the m is going to be 105.23, the mass of the water, plus 1.25 grams, the mass of the ammonium chloride. Now for the C, or the specific heat capacity, it says that the specific heat capacity of the solution is 4.18 joules per gram degree Celsius. And what about that delta T? I will just focus on the absolute value of the change in temperature. So I'm not going to do T final minus T initial. I'm not worried about positive or negative signs. I'm only focusing on the magnitude of the temperature change. So 20.00 minus 19.21, that gives me a difference of 0.79 degrees Celsius for my delta T. So my mass of solution is 106.48 grams. My specific heat capacity of the solution is 4.18 joules per gram degree Celsius. So when I pick up my calculator, I'm going to do 106.48 times 4.18 times the delta T, which is 0.79 degrees Celsius. Now, you'll notice that I've written down my answer as 351.618256 joules. That has way too many significant figures. But if you're not sure exactly how do we round off this answer to the proper number of significant figures, well, let's go ahead and take a look at part C of this question, which talks about significant figures. So part C says the following questions are related to significant figures. Circle the correct symbol or number to complete the following sentence. In the setup for the calculation of thermal energy, or Q, the value with the fewest number of significant figures is it M, C, or delta T? Well, hopefully you can see in the setup it's going to be the change in temperature, the delta T, which has only two significant figures. So 0.79 has only two significant figures, and the calculated value for Q should be reported with two significant figures. Now, in part B of this question, when I did Q equals mc delta T, I got an unrounded answer of 351.618 joules. If I round that number off to two significant figures, I would express that as 350 joules. And when I convert that from joules to kilojoules by dividing by 1,000, that would be 0.35 kilojoules. So the correct answer to question C is delta T and two significant figures. And going back to part B of this question, if we're looking for the final answer with the proper number of significant figures, that would be 0.35 kilojoules. Now, technically, on the AP Chemistry exam, if you wrote 350 joules, that is correct, but they were looking for the correct answer in units of kilojoules. So when you read the question on the AP Chemistry exam, pay attention to the units that they are looking for in the final answer. So 0.35 kilojoules, that is the intended answer to this question. All right, now let's take a look at part D of this question, and you will notice there's that symbol for the change in enthalpy. So the enthalpy of solution is symbolized with delta H of solution. So calculate the magnitude of the change in enthalpy of solution for ammonium chloride, and they would like the units to be kilojoules per mole. It says include the sign in your answer. And if you're not sure what that means about the sign, the change in enthalpy will be positive if the change is classified as endothermic, and the sign of delta H would be negative if the change in enthalpy is classified as exothermic. So positive delta H, endothermic, negative delta H, exothermic. Now, because we're looking for kilojoules per mole, it sounds like a good place to start in this calculation is to calculate the number of moles of ammonium chloride that was used in this experiment. So the number of moles of ammonium chloride can be calculated as follows. I'm going to take the mass of ammonium chloride, which is 1.25 grams, and then I will convert that from grams to moles using the molar mass. So my conversion factor will be 1 mole of ammonium chloride for every 53.49 grams. And when I pick up my calculator, it's going to be 1.25 divided by 53.49. And I'm going to leave this unrounded for the moment because normally you don't round off your answer until the final number that you get at the very end of your calculation. So at the moment, I'm going to use some extra significant figures because 0.023369, that is my number of moles of ammonium chloride. And if I go back to that unrounded answer from part B, that would be 0.351618 kilojoules. Again, my unrounded answer for the quantity of heat that was transferred during the dissolution of ammonium chloride. So kilojoules per mole, that means I'll take the kilojoules and divide by the moles. 0.351618 kilojoules divided by 0.023369 moles of ammonium chloride, and the unrounded answer is 15.046 kilojoules per mole. Now I think it would be a good time to round off my answer to two significant figures based on the fact that in part C, we are limited by the delta T, so two significant figures in my final answer. That's going to be just simply 15. Now the sign of delta H will be positive if it's endothermic, and the sign of delta H will be negative if it's exothermic. So this is an endothermic process. And so that's why I'm including a positive sign with my answer for the delta H, or the enthalpy of solution. So the dissolution of ammonium chloride is endothermic because the temperature decreases during the dissolution process. Endothermic, positive delta H, exothermic, negative delta H. So there's my answer to part D of question 9. The enthalpy of solution for ammonium chloride is positive 15 kilojoules per mole. All right, well, hopefully all of the answers and explanations to question 9 in this packet make sense. Now, before we take a look at question 10 in this packet, I'd like to show you another example of a free response question, and this one was from the 2025 AP Chemistry free response questions. This is question 3, and I'm focusing on parts C and D of question 3 from the 2025 AP Chemistry exam. So these questions involve calorimetry calculations. We can see a diagram, and that represents a calorimeter. So a chemical reaction takes place inside this calorimeter, and there's a data table, and in that data table we have information about mass, temperature, we have information about molar mass and specific heat. So the question says that solid P4O10 reacts exothermically with water to form phosphoric acid as represented by equation 2. It says the chemist carries out the calorimetry experiment and records the following information. So we have the mass of the P4O10, we have the mass of the water, we have the initial and the final temperature, we have the molar mass of P4O10, and we have the specific heat capacity of water. And it says, calculate the amount of heat released during the experiment in kilojoules. Assume that the specific heat of the solution is the same as that of water. So we're going to use the Q equals mc delta T equation, and the M represents not just the mass of the water, not just the mass of the P4O10, but the entire mass of the solution. So that would be not just 0.100 grams, not just 100.0 grams, but the combined mass, 100.0 grams of water plus 0.100 grams of the P4O10. Now for the specific heat capacity of the solution, it says assume that that is the same as that of water, which is 4.18 joules per gram degree Celsius. And the change in temperature would be the difference between 22.00 and 22.38 degrees Celsius. So that's a difference of 0.38 degrees Celsius. So just like we saw in the previous question from this packet, we have a delta T that has only two significant figures. So when I do this math, 100.1, the total mass of the solution, times 4.18, the specific heat capacity, times 0.38, the change in temperature, on my calculator, I get an unrounded answer of 158.99884 joules. Now, if I round that off, instead of rounding it off to 159, I'm going to be limited by the two significant figures value of my delta T. So I'm tempted to say 159, but in fact, the value of Q should be reported with two significant figures. So it's not going to be 159, it's going to be 160, and that's 160 joules. Or if we need to report our answer in units of kilojoules, that would be 160 divided by 1,000 to go from joules to kilojoules. So I would accept either 160 joules, but the intent of the question, what I'm looking for, is 0.16 kilojoules. Let's take a look at the official scoring guidelines for this question. So you can see on the official scoring guidelines, and I will make sure that you have access to all of these questions and the scoring guidelines in the video description area, it says, for the correct calculated value, reported with the correct number of significant figures. So 0.16 kilojoules, that was the intended answer. So there's the intended answer highlighted in green on the right side of this slide. And now you can see examples of common mistakes that were made on this question. So one mistake was the incorrect use of the mass. So the students used only 0.1 gram for the mass of the solid and not 100.1 grams, the entire solution's mass. And then they reported the final answer that was correct, perhaps 159, but they did not express their answer with the proper number of significant figures. So this answer should be reported with two significant figures as 0.16 kilojoules. Now, the next part of this question switches from Q, or thermal energy, to delta H, the change in enthalpy for this reaction. So it says calculate the value of the delta H, or the change in enthalpy for this reaction. It says to include the sign in your answer. So remember that positive delta H, endothermic, negative delta H, exothermic. Let's go ahead and calculate the number of moles of P4O10. So we have 0.100 grams of P4O10 that reacted in this experiment. And we don't need to use the periodic table to calculate the molar mass of P4O10. It's actually given to us in this table. So I'll go ahead and set up my conversion factor to go from grams to moles. It's going to be 1 mole of P4O10 for every 283.9 grams. So 0.100 divided by 283.9 gives me a very small number. I will express this in scientific notation. So my number of moles is 3.52 times 10 to the negative 4 moles of P4O10. Now, if I take 0.16 kilojoules and then I divide by the number of moles, I will get units of kilojoules per mole. Now, it actually says kilojoules per mole of reaction, but I will talk about mole of reaction in my next episode of AP Chemistry Review and Practice. So the concept of mole of reaction will be explained when I get to topic 6.6, Introduction to Enthalpy of Reaction. So based on this calculation, 0.16 divided by 3.52 times 10 to the negative 4, there is my answer, 450 kilojoules per mole. And if you're thinking, shouldn't the sign of delta H be negative, you are correct. So we are looking at an exothermic reaction. If the temperature of the reaction mixture increases, then thermal energy is released and the process is exothermic. So yes, this reaction is exothermic because the temperature increases as the reaction proceeds. So the correct answer for the delta H should be negative 450 kilojoules per mole. I will show you the official scoring guidelines for this part of the question. You can see there is the Q, the 0.16 kilojoules, and they're showing a negative sign because it's exothermic. And then there's their calculated value, negative 450 kilojoules per mole of reaction. Now, as far as the mistakes that students made on this particular question, there was misunderstanding about how to calculate the delta H of reaction from the Q value, and trying to use a different formula involving reactants and products to calculate delta H, but this information was not provided in this question. And not including the negative sign for delta H was another common mistake. Now, there was one more part of this question that I wanted to mention. So this question, which is listed below the data table on this slide, says the following. The chemist weighed out 0.100 grams of P4O10 and 100.0 grams of water to perform a second trial. But in the second trial, some of the solid P4O10 stuck to the weighing paper and was not transferred to the calorimeter. Now, given that P4O10 is the limiting reactant, would the value of the change in temperature, delta T, for the second trial be less than, greater than, or equal to the value in the first trial? Justify your answer. So less solid P4O10 was added to the calorimeter. A smaller amount of thermal energy is released during the reaction. So therefore, the delta T for the second trial should be less than the value of delta T for the first trial. Let me go ahead and show you the official scoring guidelines answer for this part. So the answer is less than in terms of the delta T comparison. So if less P4O10 is present, less thermal energy will be transferred to the water during the reaction, causing the temperature increase to be less than it was in the original trial with 0.100 grams of P4O10. And as far as common mistakes that students made, so students wrote an explanation that implied that it was a warm solid being placed into water that caused the delta T. So not a chemical reaction, but a hot sample of solid added to cooler water. So that was an incorrect explanation because it was a chemical reaction. It wasn't a warm solid placed into water. And then another mistake that was very common is there was no information about connecting the thermal energy to what happened in terms of the event. The students simply said there's less solid, so less delta T, but they never talked about a smaller quantity of heat or thermal energy. All right, well, those were the answers and explanations to FRQ, free response question number 3, parts C and D from the 2025 AP Chemistry exam. I just wanted to include that in this episode because these questions were related to topic 6.4, heat capacity and calorimetry. Now let's go ahead and take a look at question 10 in this packet. So as you can see on this slide, questions 10 through 12 refer to the following information. A student adds a sample of water to a calorimeter and adds a sample of solid potassium chloride. stirring to dissolve. After the potassium chloride dissolves completely, the minimum temperature reached by the solution is recorded, and the data from the experiment are shown below. So we can see a data table with mass of water, mass of solid potassium chloride, initial temperature, and final temperature. So question 10 says the mixture in the calorimeter has a specific heat capacity of 3.95 joules per gram degree Celsius. Based on the data from the experiment, the magnitude of thermal energy, Q, transferred in the dissolution of potassium chloride is closest to which of the following? So because we need to calculate the magnitude of thermal energy, Q, let's go ahead and use the Q equals mc delta T equation. And for the m, it's going to be not just the mass of the solid potassium chloride, not just the mass of the water, but the combined mass of the solute and the solvent, the mass of the entire solution. So not just 10 grams, not just 100 grams, but 100 plus 10, so 110 grams of solution. And the specific heat capacity of the solution was given as 3.95 joules per gram degree Celsius. And the change in temperature is the difference between 25.00 degrees Celsius and 19.70 degrees Celsius. So that's a difference of 5.30 degrees Celsius. So we have 110 grams of solution. So 110 times the specific heat capacity, 3.95 joules per gram degree Celsius, times the delta T, 5.30 degrees Celsius. And when I put those numbers into my calculator and multiply, I get 2,302.85. And if I divide by 1,000, that would be 2.30285 kilojoules. I am limited by the delta T, which has only 3 significant figures, and my value for specific heat capacity also has 3 significant figures. So the value of Q would be reported with 3 significant figures as 2.30 kilojoules. So that makes choice B the correct answer to question 10. Now, questions 11 and 12 will still relate to this laboratory situation. Let's go ahead and take a look at question 11. In question 11, it says that the student weighed out 10.00 grams of potassium chloride and 100.00 grams of water to perform a second trial. But in the second trial, some of the solid potassium chloride stuck to the weighing paper and was not transferred to the calorimeter. Which of the following correctly predicts how the value of delta T for the second trial would compare to the value of delta T in the first trial and provides the correct justification? So I wrote this question to be similar to part D of question 3 from the 2025 AP Chemistry exam. So we have less solid potassium chloride that was added to the calorimeter, therefore less thermal energy, a smaller amount of thermal energy is transferred, and that would result in a smaller value for delta T for the second trial compared to the value of delta T for the first trial. Since the value of delta T in trial 2 will be less than the value of delta T in trial 1, that means that the correct answer to question 11 is either choice A or choice B. So let's go ahead and eliminate choices C and D, which says that the value of delta T will be the same as trial 1. Now, with respect to the justification, we can see that in choice A, it says the mass of KCl is directly proportional to the magnitude of delta T. And hopefully you will realize that that is an insufficient justification because there's no mention of the thermal energy of dissolution. So the valid justification that we're looking for normally involves an explanation of chemical principles. So on the AP Chemistry exam, students must do more than simply state the relationship between two variables. They should make that connection between what's happening at the reaction or the dissolution or at the particle level with what is observed in the laboratory in terms of at the macroscopic level. So a better justification for why the value of delta T in trial 2 will be less than the value of delta T in trial 1 is what is listed in choice B. If less potassium chloride is added to the calorimeter, less thermal energy will be transferred during the dissolution of potassium chloride. So that is a better justification for why the delta T will be less in trial 2. So the answer to question 11 is choice B. Now let's go ahead and take a look at question 12, which is still related to this same calorimetry experiment involving potassium chloride. So question 12 says the following. The student conducts a third trial of the experiment, and the data from trial 3 are shown in the table below. Now you will recall that in trial 1, 10 grams of potassium chloride was used, but here in this trial, 5 grams of potassium chloride is used. And the question says, which of the following correctly predicts how the calculated values of Q and the delta H, or the change in enthalpy of solution, associated with the data for trial 3 will compare with the values from trial 1. So we have the calculated value of Q in trial 3, and then we also have the calculated value of the enthalpy of solution in trial 3. So what you should be thinking about is when I add only 5 grams of potassium chloride to the water, instead of adding 10 grams of potassium chloride to the water, how will that affect these results for both Q and delta H? So back in question 10, we had a calculated value for Q of 2.30 kilojoules. Let's go ahead and repeat that calculation, but this time using 5 grams of potassium chloride. It will still be the total mass of the solution, which is the sum of both the potassium chloride and the water. That would be 105 grams of water plus 5 grams of potassium chloride. So that is a total mass of solution of 110 grams. We assume that the specific heat capacity of the solution is the same as what was mentioned in question 10, so 3.95 joules per gram degree Celsius. And as far as our delta T is concerned, it would be the difference between the initial and the final temperature, so that's 25.00 degrees Celsius minus 22.35 degrees Celsius. That's a difference of 2.65 degrees Celsius. So when I pick up my calculator and check this math, 110 times 3.95 times 2.65, I get approximately 1.15 kilojoules. So 1.15 kilojoules, how does that compare with the value of Q from question 10? Hopefully you can see that the value of 1.15 kilojoules in trial 3 would be less than the value of 2.30 kilojoules in trial 1. So we know that the calculated value of Q in trial 3 will be less than the calculated value of Q from trial 1. Let's go ahead and eliminate choices C and D because it's not the same as, it will be less than. So I'm going to go ahead and eliminate choices C and D. Now, as far as the calculated value of the enthalpy, or the change in enthalpy delta H for the solution, it is based on the number of moles. So if we used 10 grams of potassium chloride in trial 1, but then we used only 5 grams of potassium chloride in trial 3, there's going to be a different number of moles. I'm going to go ahead and show you the molar mass of potassium chloride, which comes from the information on the periodic table. And to calculate the number of moles of potassium chloride, that would be 10 grams divided by 74.55, 5 grams divided by 74.55. So clearly we have a different number of moles, but watch what happens when we take the heat, or the number of kilojoules, and we divide by the number of moles. So maybe you can already anticipate what's about to happen in this calculation for the delta H of the solution. If I have half the number of grams of potassium chloride in trial 3, I will get half the number of kilojoules for Q, but I also get half the number of moles of potassium chloride. So you can go ahead and do these calculations on your calculator and just verify that the value of delta H for trial 1 is 17.2 kilojoules per mole, and the value of delta H for trial 3 is also 17.2 kilojoules per mole. So because we have cut the number of kilojoules for Q in half, and we've also cut the number of moles of KCl in half, we get the same ratio of kilojoules per mole. So the correct answer to question 12 is choice B. that the value of Q will be less in trial 3 than trial 1, but the value of delta H of solution will actually be the same in trial 3 as it is in trial 1. So I wrote this question just to remind you that we have more coming in our next episode of AP Chemistry Review and Practice. For topic 6.6, enthalpy of reaction, we will have more to say about Q and delta H. All right, now we have come to the part of the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice for you is if you're looking for more practice problems or you need more background information about topics 6.1 to 6.4, then check out this video for topics 6.1 to 6.5, and you can find that link in the video description area as well. The next piece of advice I will give you is what I normally say at this part of the lesson. Read the question carefully and make sure you are answering the question that is being asked. My next piece of advice is to remind you about the temperature change and the situation between system and surroundings, that the thermometer is usually considered to be part of the surroundings. Therefore, if you discover that during the chemical reaction or the dissolution of a solid, the temperature decreases, then that would be an endothermic process. And the example is an instant cold pack. On the other hand, if you discover that during the chemical reaction or the dissolution of a solid, the temperature increases, then that would be an exothermic process. And here's the example of the instant hot pack. Dissolving an ionic solid in water involves a combination of breaking attractive forces and forming attractive forces. Breaking attractive forces is an endothermic process, such as breaking the attractions between the ions in the solute or breaking the attractions between the solvent molecules in the solvent. And then forming attractive forces is an exothermic process, such as forming attractive forces between ions and polar molecules. If you are given an energy profile diagram, you can classify the reaction as endothermic or exothermic by comparing the potential energy, or enthalpy, of the products with that of the reactants. So if the potential energy of the products is greater than that of the reactants, then the reaction is endothermic, like in this diagram. On the other hand, if the potential energy or enthalpy of the products is less than that of the reactants, then the reaction is exothermic, like this diagram. Some diagrams may appear similar to an energy profile diagram. So just be careful. A graph may be used to show the change in temperature that occurs during the course of a chemical reaction or during the dissolution of a solid. So if you see a diagram that shows an increase in temperature that occurs during a chemical reaction, this is not the same as the energy profile of an endothermic reaction. So watch out for that. The Kelvin temperature of a sample of matter is proportional to the average kinetic energy of the particles in the sample. If two substances are at the same temperature, they have the same average kinetic energy. Thermal energy, or heat, is the energy that is transferred from a warmer object to a cooler object. When a hot metal sample is added to a cooler sample of water, assuming that no heat is lost to the surroundings, the following statement is true: the heat lost by the metal is equal to the heat gained by the water. Now, compared to most metals, water has a higher specific heat capacity and would experience a smaller value for delta T. On the other hand, compared to water, most metals have smaller specific heat capacity values and would experience a larger value of delta T. On the AP Chemistry exam, the specific heat capacity is normally expressed with units of joules per gram degree Celsius. The specific heat capacity is always expressed as a positive value. When performing calorimetry calculations related to the equation Q equals mc delta T, pay attention to the units in the setup for your calculation. If you see a laboratory experiment involving the enthalpy of solution, consider the following guidelines. The mass in the Q equals mc delta T equation should be the mass of the entire solution, the mass of the solute plus the mass of the solvent. The specific heat capacity of the solution may be the same as or similar to the heat capacity of water, which is 4.18 joules per gram degree Celsius, but you should still use the mass of the entire solution in your calorimetry calculations. You can calculate the change in temperature as T final minus T initial. Make sure to use the change in temperature. Some students make the mistake of using the initial temperature or the final temperature instead of the change in temperature. Now, I personally consider that the thermal energy or the heat, Q, is a magnitude of energy in joules or kilojoules. I don't think of it as a change in energy. Therefore, I ignore the sign of Q in my calorimetry calculations. I normally express the numerical value of Q as a positive number, that is, the absolute value of the thermal energy. Now, if the temperature of the solution decreases during the dissolution of the solid, the process is endothermic, and if the temperature of the solution increases during the dissolution of the solid, the process is exothermic. A valid justification normally involves an explanation of chemical principles. To earn credit for their response, students must do more than state the relationship between two variables. They must make a connection between what happens at the particle level during a certain chemical event to the observations made in the laboratory or the predicted results of an experiment. In most calorimetry experiments, we assume that the calorimeter is perfectly insulated. If heat is lost from the calorimeter to the surrounding air during a reaction or a process, then this would result in a smaller calculated value of delta T, and this would cause the calculated value of Q to be smaller than the actual value. Now, with respect to significant figures, the most common application of the rules for significant figures involve multiplying and dividing. The measurement with the fewest number of significant figures determines how many significant figures should be used to express the calculated value. And the rules for significant figures that involve addition and subtraction focus on the precision of the measurement devices. For example, electronic balance, thermometer, graduated cylinder, etc. If two measurements have different levels of precision, then the measurement with the fewer number of decimal places determines the number of decimal places that should be reported in the calculated value. All right, just a couple more of quick examples of some free response questions that I found that are relevant to this lesson. So this was from the 2024 AP Chemistry exam, and this is FRQ number 1, part E. In part E, it talks about an experiment in which 100 milliliters of a 0.500 molar lactic acid solution is combined with 100 milliliters of a 0.500 molar sodium hydroxide solution. The density of each solution is assumed to be 1 gram per milliliter, so 100 plus 100 is 200. So that would be a total mass of 200 milliliters, or 200 grams when you multiply the density by 1. So 200 grams of solution. The specific heat capacity was given as 4.2 joules per gram degree Celsius, and the change in temperature, it goes from 20 degrees Celsius to 23.2. So that's a difference of 3.2 degrees Celsius. So 200 times 4.2 times 3.2, that gives us 2,688 joules, which would round off to two significant figures as 2,700 joules. So in 2024 FRQ number 1, part E, the correct answer for the first part was 2,700 joules. And you can see there's the official scoring guidelines answer for that part of the question. Now, with respect to the common mistakes that students made, the most common error was using the molarity and volume to solve for moles of solute. So instead of considering the entire grams of the solution, students incorrectly calculated the number of grams of just the solute that was dissolved. There were also some algebraic errors, and some students, instead of using 3.2 degrees Celsius as the difference in temperature, or delta T, they used the final temperature, 23.2, as the change in temperature, which was incorrect. And with respect to the enthalpy of the solution, that would be 2.7 kilojoules divided by the number of moles. So the number of moles involves volume times molarity for one of the reactants. And so the reaction is exothermic because the temperature increases from 20 degrees Celsius to 23.2 degrees Celsius. Therefore, it should be a negative delta H. So the delta H was negative 54 kilojoules per mole. And there's the official scoring guidelines answer for that part of the question. This is FRQ number 1 from 2024, part E. And again, as far as examples of common mistakes, students forgot to include that negative sign for the enthalpy. It was an exothermic reaction, so the delta H should have been negative. And then they calculated the moles of each reactant and they added them together. So they used the total number of moles instead of the moles of just one of the reactants. So again, that's more of a stoichiometry mistake in terms of the chemical reaction. And the last part of that question that I wanted to mention is it says, the student claims that if heat is lost from the calorimeter to the surrounding air during the reaction, then the experimental value of the molar enthalpy of reaction will be smaller in magnitude than the actual value. And that is a good claim. So I would agree with the student's claim that if heat is lost to the surrounding air during the reaction, that would be a smaller value of delta T, a smaller value of Q, and therefore a smaller value of delta H. So the mistake that a student made in this one was, the most common mistake was simply repeating the prompt that if heat is lost, then the molar enthalpy is lower, but they didn't actually talk about the experimentally measurable quantity, which is the temperature. So you must connect observations from the laboratory to what's happening. So not just a generic statement which says less heat and therefore less molar enthalpy. So they had to connect the experimentally measurable quantity, which was the delta T, the change in temperature, and then connect that to the delta H to earn that point. Now, in 2019, there was a procedural question where the students had to list the specific measurements that are required for enthalpy of solution. And the answer to 2019 FRQ number 1, part E, was you have to measure the mass of the solid, the mass of the water, the initial temperature of the water, and the final temperature of the solution. So the mass of the solid, the mass of the water, initial temperature of water, and final temperature of solution. So mistakes included writing a procedure instead of listing the actual measurements, taking the initial temperature measurement after the urea or the solid has already been combined with the water, instead of measuring the temperature of the water before the solid is added. They would often omit the mass of the water. They just said the mass of the solid and nothing else as far as the mass. They would use laboratory equipment to record derived quantities such as delta T. You can't measure delta T. You can't measure Q. So you can measure initial and final temperature, and you can measure the mass. And they were confusing heat and temperature. So they would say measure the heat instead of measure the temperature. All right, I would just like to say I apologize for the length of this video. I just had so many good examples from calorimetry that I wanted to share. So I do understand that this video, this episode of AP Chemistry Review and Practice, was a little bit longer than my usual videos in this playlist. So yes, now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 6.5 and 6.6. If you enjoyed this lesson, thank you very much. I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include all of those free response questions and scoring guidelines, and it also includes the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. And I definitely want to say thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.